Hello, my name is Louis. I'm from Boston College, and this is a joint work with Kishori and my postdoc Saptap. Our title is a pretty long, but it will make sense. It's called Semi-Fast Byzantine-tolerant Shared Register without Reliable Broadcast. And the motivation is that we have distributed database, we have servers, and we have tons of clients, and jointly they need to write some data and read some data in the databases. And the reason that we want it to be distributed because we want to have a lower latency, scalability, and higher availability. And here we focus on the concept of a key value storage, or in the terminology of more theoretical setting is a atomic register or shared register. And for practical systems like we have Amazon Dynamo, Cassandra, React, which are kind of more practical implementation of this kind of abstraction. So what's the model? It's called read-write register or read-write data object. Like we can call it a shared key value pair. So we have two things that we want to care about. One, the first one is K, which is the key, and V is the value. So that's your data model. That's how you store inside the servers. And we only provide two very simple APIs. The first one is read, and then you need to specify the key K, and the server will return the value to you, and that's the V, that's something you want to read. And we also can do a write where you specify the key and then you update to a value V. Okay. And in our model, we have asynchronous networks because for internet, asynchrony is a very appropriate model. And we have servers and client. And the full model following the convention, like we assume a Byzantine server, so Byzantine 40 server can do arbitrary things. And for the client, we will assume that they are cross-prompt. Okay, so they cannot do anything as arbitrary. Instead, they need to follow the specification of the protocol unless they have crush, and one they can crush at any point of time. So that's our full model. And there are tons of prior work that already explore in this area. Some of the earlier one, like the seminal work by Hagit, is Atiyah, Barnoy, Dolev, Jason paper. That's the first one that kind of implement this atomic share register in this kind of setting. They assume the crush 40 servers, but that it's a phenomenal result. And after that, like people have studied different verification, and most related one is that this DSM work. They also assume that this Byzantine 40 server, and then the crush tolerant or crush prone clients, and they design a protocol called small Byzantine quorum. And later on question caching, they extended, or like they designed a new thing called like use erasure coding. And later on there's also the notion try to improve the latency, so they introduced the notion of semi-fast. And then later on Jennifer, the group from TAMU, they also have this Byzantine multi-writer regular register. So all this long history inspired our work. And what's the new angle? What's new inside this paper? The key observation that we made is that all the prior work, that they have a fantastic, awesome result, but they assume that everything, the underlying network, is very powerful, that they provide this kind of reliable broadcast abstraction, is that you have this eventual all or nothing property. So intuitively, is if a correct node or if a forthright node receives some message M, then eventually all the forthright nodes, they will receive M. It's a very powerful model because that if I'm good, I receive something, then I can be sure that eventually if you are good, you will also receive something. And then the other properties, I suppose I'm a sender, I'm a client, because I'm always good, so that I can assume that always the server can eventually receive something that I send. Okay. And if you think about it, yes, if you assume that TCP is behaving nice, then yes, we have this property. But like sometimes if the internet is not very stable, if the networking has some weird thing, or even like the networking is Byzantine itself, then this reliable broadcast abstraction actually is not that easy to be ensured, to be implemented. So if you assume a peer-to-peer network without any kind of hardware support, then the best protocol that we can implement RB, reliable broadcast, is that you need to have at least 3 message delays. So message delay is kind of longest latency that you send a message from one end to the other end. So if you look at all the prior storage protocol or shared register emulation protocol, they need that at least 3 times 2 message delays. The reason we have 2 is that if I send you something, then you send back. That's how I get a message, and then all of them rely on reliable broadcast. And then for more standard protocol, it's like typically 2 round trips. So everything would be like 3 times 4, that's at 12 message delays. And then for many of the application for distributed storage system, actually that will already be too long. So the motivation is that can we get rid of reliable broadcast and still provide useful guarantees? So this work, we don't assume any kind of reliable broadcast abstraction. And let me introduce some typical parameters. We have n, which is a number of nodes, or sorry, number of servers inside the system. We don't really care about how many clients are there. And we have f, is the upper bound on the number of Byzantine servers. And we propose a algorithm. It's a multi-writer, multi-reader, and it's a replication base, meaning that each server has exactly the same copy of the data, and we provide the guarantee that's called safe. And then our read operation is called one-shot. Okay, so that meaning that it's a one round delay, one round trip delay, then we are done. And then that's the reason that it's called semi-fast, because our write is still two round trip. Okay, and one downside is that our n has to be strictly greater than 4f. And if you remember what I talk about replication, is that every server that needs to have exactly the same copy. And sometimes if the data is too large, then you are kind of wasting space. So we also improve this to be an erasure coding based one. Then we need to have f more servers. And the other downside is that there's only single writer, and it's an open problem on how to extend that to multi-writer. Okay. So that's our contribution for the positive side. And then for the negative side, we prove that actually 4F is what you need. It's a necessary condition to implement safe register if you don't want to use reliable broadcast abstraction. Okay. So now here are some preliminaries. So what's operation? Typically operation is a read or write, and then it's marked by 2 events. Usually in the figures or in the illustration, we draw it as a box. So there's an invocation event. It's where on the left-hand side, that's where you start. That's we call it invocation. And then this on the right-hand side, the right side is the time is terminates. That's called a response event. Okay. So it's a box full operation, and we have invocation and we have response. Then we call operation concurrent if that they are overlapping with others in real time. So remember, it's a distributed system. So for the client, 2 clients, they try to issue the read or write operation at the same time, then you will have concurrent events, concurrent operations. And then one very important notation or the notion for consistency is that the precede. So in this case, because operations response event happens before the invocation event for operation 2. So that's when we call operation 1 precedes operation 2. So now that we know this notion, then we can introduce the safeness guarantee. The safe is one of the more typical consistency guarantees. And in the more system or practical literature, sometimes we also call it strong consistency. So here is a multi-writer, multi-reader, meaning that we can support multiple writer clients and multiple reader clients. And then we say that the register or the emulation algorithm or the implementation is safe if that for any read that is not concurrent with any write returns the value of some write that precede R, as long as no other write fall completely between W and R. Okay, I know it's verbose, but I try to remember it. I'll show you some example later. Then if this condition is not satisfied, then this register can return arbitrary values. Usually it just return the default value. So here's an idea. If your operation looks like this, then the read operation has to return 1 because W1 precede your read operation. Then if you look like this, because that R and W, they are overlapping, so the precondition of the first I is not satisfied, so R can return either 0 or 1, or like where 0 is a default value. And then if you have this 1, 2, then R it returns 1. And then if somehow the preceding operations that they are concurrent write operations, then R could return 1 or 2 or default value, it's fine. So it's sometimes that you might think it's a bit weak, but actually it's already very useful in many of the practical systems, especially when there's a Byzantine failure. And one-shot read, what is one-shot read? One-shot read just require each read operation completes in one run of client to server communication. So if I send something and then server doesn't need to communicate with any other server, they can just immediately reply to client. So there's no internal delay, and then that's called one-shot read, and our protocol achieves one-shot read. So yep, here's a illustration. So the client will send something to the server, and then the server, just like does internal computation, it doesn't need to communicate with any other server. It can directly send it back to the client, and as long as that client is able to receive enough reply from the server, then the read operation is complete. Okay. And now let me introduce our key algorithm called BSR, Byzantine Safe Register. And I will also use a working example with n equal to 5, f equal to 1. So remember our algorithm need to have at least 4f plus 1. So n equal to 5 is the smallest number of server that we need. So the first thing is that client, when they try to do the write operation, it first need to get a tag. So what it does is that it sends a message to all the servers, and then the server will just return something to it. And because it's a asynchronous nature, so we can wait for at most n minus f servers. And then the Byzantine server can send arbitrary data to the client. And then when you collect all those, you update the tag to be the f plus 1th largest or highest tag among response. So in this case, because that you are waiting for at least 4 server response, so the client will be able to see 2. So the tag, the client will be able to see at least 2 2s. And remember what's f? F equals to 1. So your tag must equal to 2 in this case. Then when you want to put the data, you will create a new tag here. So it's equal to 3. So now you will send next thing. Let me use a color red here. So in the next phase, when you want to update or you want to put data into a server, you will write like 3 and then your writer ID, and then V. That's what you are going to send to the server. And then upon receiving this write request, server will send an ACK to the client. So send an ACK client, and then client will need to collect it again and minus f x, then it's complete. So that's the write operation. And now let's look at what happens to the server side. So the server side actually pretty simple. It will keep a list. List is that you have a list timestamp and then the values initially null. So when you say that, okay, when the server receive a get tag request, it will just send the maximum timestamp that it knows. So in this case, the server will send 222 to the clients. And then when it receive the put data thing, it will check if this incoming message is the highest, then you will include in the local list. Otherwise, just I send a ACK to the writer. And then the get data response is in this case, it just look at the head of the list, meaning the one with the largest timestamp, then send it back to the client. Okay. Then for the read, remember that we can only do one shot. We want to achieve one shot read, so that just like 2 message delay. So first you send the query data to the server. So let me draw it again. So the first thing is a client said, hey, I want to know what data you have. And then the server, in this case, suppose this 2B, 2A, 1A is the thing that they know that's most recent. Then they will send this thing back to the clients and this thing back to the client. And then the Byzantine server, again, will send arbitrary things. Then you wait for n-f servers, and then you introduce notion of set P, which is the set of witnesses. So in this case, this server is a witness of 2B, this server is a witness of 2A, this server is a witness of 2A, so on and so forth. Okay. Then in this case, suppose that this is the third server, will also reply this 2A back to the client. Then you will see that, oh, okay, that's pretty good, because that you have a witness of like this two values. Then you just add this 2A into set P, and then this TRVR would be the one with the highest tag. So that's the TRVR here. It's equal to 2AB here. And then the next if condition, you check that, okay, if this is non-empty and this TRVR is greater than the local values, then you update it, then you will return value V local. So very simple protocol, and then it achieves regular, safe semantics. Okay, so that's the algorithm. Now let's look at, look at the proof sketch. So the first thing we want to prove that the f+1 thing actually works. So the lemma is that for each pair of read and write, then if W completes before R begins, then the timestamp of W must be less than or equal to the timestamp of R. Okay. And then because of lemma 1, we can use to prove lemma 2. Lemma 2 is that the way we define a timestamp, and then we can totally order all the timestamps, and then those things will respect the real-time ordering, because that's the way we construct the timestamp. And then the next one is that for each read operation, we can always find some low R such that that's the value that R returns. Okay, and then this R could be something that precede R equal to 1 in this case, or it could be 0, which is the default value. And okay, then our the safeness property, basically that we can use this lemma 1, lemma 2, lemma 3 property to prove it. And then the idea is that we need to consider like different cases. And one of the key case that we want to consider in this case, when I have r equal to 1 and when I have w equal to 1. And the reason is that when w1 occurs, then it must be the case that it has the value that's stored inside at least 3 servers if I f equal to 1. Then if that's the case, when r equal to 1, it will hit at least 2 of the servers that will be able to send be the witness of this write, and then this r will be able to see that value. And then that's one of the key case that we want to we prove in the paper. So that's the intuition. And then the next one is that we actually show the paper inside the paper that the BSR, even though it's pretty simple, it does not satisfy regularity. And then in order to satisfy that, we need to send the entire history. That's one way to do that if we want to do semi-fast or one-shot read. Otherwise, we need to have 2 wrong reads if there are concurrent writes. So like for the writer, it's always possible to detect that they are concurrent write. And I think that the second one would be a very practical solution. And we also have erasure coding, and the concept of the intuition is similar. The new trick is that we use this linear NKMD as erasure code, and that will be able to do some like kind of fault detection and fault correctness. And the good thing is that the storage cost is 1 over K inside the server. But the downside is that we need to have F more servers, and then it can only support single writer right now. And it's an open problem on whether we can improve it or not. So now let me briefly talk about the lower bound. So why do we need so many nodes? And the key observation listed as lemma 5, lemma 6, lemma 7 in the paper is the first one is that when we try to return something, we need to have at least f plus 1 server. Intuition is very simple because if you can return something that's only seen by the f servers, then basically Byzantine server can tell you anything. Then you don't want that. And then the next one is m minus f thing. So the life list is that even if some server crash or some server become Byzantine-40, you still want to make progress. So if you need to wait for more response from the servers, then of course you cannot progress anymore because the server might just crash and never respond to you. And the final lemma that we see is that the safety cannot be guaranteed if the write operation do not communicate with at least 3F servers. And the idea is that somehow you need to ensure enough number of servers that have your data inside the system, and otherwise that you will have a kind of be lied by the Byzantine servers, and then Byzantine server will outweigh the good servers. Okay. So now we have these 3 lemmas, and then let's see how we can prove the lower bound. It's actually pretty simple. So we want to prove that it's impossible to achieve to implement safe register when n is strictly less than 4f plus 1 if we don't use any reliable communication. Here we model it as that there's no server to server communication. So now suppose n equal to 4f, and we want to prove that we will get a contradiction. Then suppose the writer, because lemma 6 and lemma 7 tells you that in this case, writer can only contact 3 servers. And suppose that writer get the response from the first 3 server, and it writes at 1 AV. So Byzantine server just say, hey, I got it, but I throw away the update. Okay, and then this server somehow is slow, or the message is lost, so this server doesn't receive anything. And then that's the key difference because we don't assume RB. And I will tell you what happens if we have a reliable broadcast later. And now for the read, what you get is another reader. The response you got is for this first two servers, and then this server that got delayed. So suppose the Byzantine server tell you that, hey, I don't have anything. So that's from the Byzantine server. And then this is from server 2. And then this is from the server 4. So it's possible that the reader get these three values. Then in this case, one of the lemma, is a lemma 5, said that if you return 1AB, then it's possible that this is a faulty value, so you shouldn't do that. Then what you can do is that you can only return the default value because the first server and then the fourth server tell you that, hey, there's no update. But then in this case, it violates safeness because that, remember, the writer's write already completes, then that's the only value 1A that you want to return. Okay, so that shows that 4F plus 1 is the lower bound. Okay. Then what happens that if we have a reliable broadcast abstraction? The idea is that because if you remember at the very beginning, I told you that this eventual or nothing property, because that this guy received 1A, this guy received 1A, so eventually this server will also receive 1A. Then typically for the algorithm, what you can do is a reader just keep waiting until it receives enough witnesses. So in this case, it just wait on server 4, and server 4 will be able to forward the reader 1A, then at that time you can return. But like this kind of relaying, forwarding, or waiting, or the abstraction of reliable broadcast might not be the most practical thing to do in practice. So the summary is that the prior work, they are based on reliable broadcast abstraction, and which adds more latency. And for our paper, we showed that with n strictly greater than 4f, then BSR, we present the algorithm BSR, it doesn't require RB, and then it achieves the safeness property. And necessity is that the n greater than 4, strictly greater than 4f. Unfortunately, that is it is necessary. And then our result also, we also present result that based on the erasure coding storage. That's all. Thank you, and hope to see you in ICDCS.